In this video, we'll be going over acid strength, and we'll be looking at Ka to try to determine acid strength, the equilibrium constant for weak acids to try to tell. Okay, so strong acids, this is the major difference, and it's pretty basic actually. It's surprisingly basic, and you'll see it amounts to something a pretty simple request that I have for my students. So strong acids, that's what they do. They completely dissociate in water. So they have a full molecule, and then this is our full molecule is the HCl, and it fully dissociates into. You'll see that one of these H's will join together on the water and make H3O, and then the anion is also dissociated. So the ions dissociate. This actually skipped a step. It kind of shows that the hydrogen here will attach to the water. It'll do so with this reaction. So it'll be so here's your water molecule, and you have the two ions like that, and then this actually has an affinity for these, or we should probably say the lone pair electrons have an affinity for this, and likewise this. So it sticks together and it makes the H3O ion, which is the hydronium ion. And you'll see that when we start looking at and calculating pHs, that pH is calculated by taking the negative log of the concentration of H3O, the concentration of H3O. So if you have a strong acid and the starting concentration are equal to, say, like a weak acid, and you have the same concentration, you should expect more H3O to form because you'll get more ionization, and it'll react instantly with water and make the hydronium ion. And when you take negative logs of larger and larger numbers, you get smaller results. So you'll get a pH between 0 and 7 for acids. So you'll notice the key thing I said also was it depends on the starting concentration. So we'll look more at that as we move on in this chapter. So I just wrote where that comes up, so I'm going to erase what I had. So 100% exists as products, and when it comes to equilibrium, you cannot make a equilibrium constant, because if you try to write an expression, let's look and see what happens. You would have H3O times Cl minus over the concentration of HCl. Water is a pure liquid, so that's not included in the equilibrium expression. So at equilibrium, since 100% of this goes towards the ions, you would have 0 concentration here. So if you tried to do that math, your result would be undefined. So that's why it's not appropriate to even discuss equilibrium constants with strong acids. So which acids are weak are those acids that are not strong. So what this boils down to, a lot of acid-base chemistry is actually this one simple thing. You need to know the 7 strong acids by heart. I cannot emphasize it enough. It makes it so much easier to do acid-base chemistry if we just pretty much stop right now and make sure you memorize them at the very, very beginning. So there's 7. The halogen acids, except for HF, nitric acid, chloric acid, perchloric acid, and sulfuric acid, the first proton. The second one's actually weak. So what does it mean to be weak then? So it means only some of it dissociates in water. So the equilibrium will lie strongly to the left, and it'll favor the molecule form of the acid. So here we have acetic acid, and then these are the ions it makes. So as we know, as we just pointed out in the first example, the H plus breaks off and it immediately forms H3O. So most will exist in molecule form at equilibrium. So how much goes over here is the question with weak acids. How much of it, how much of this starting amount, let's say you had 1 molar, how much of it comes over here? So you need to know the Ka and the initial amount to determine that. So you would have to know Ka and the initial amount of your acid. So I'll write HA for just a generic acid and that 0 meaning initial. So you need to know those two numbers to figure out how much these make at equilibrium at EQ and at EQ. So weak acids can be ranked according to their Ka. So if you assume that these are all the same, you can rank them based on how strong they are based on their Ka. So the larger the Ka, the more ions it will stand to form. So the analogy I have is if you have so for strong acids, it's kind of like an elephant getting on a teeter totter or seesaw, and then like a little kid is sitting here. Okay, and when the elephant gets on, not only is the kid not only will it shift down, but it'll shift down so far and so forcefully the kid will just fly off the teeter totter. If you have a weak acid, so this is a strong acid, and there's 7, so it's HCl. I like to list the halogens, HI. Then I go through the polyatomics: nitric, chloric, perchloric, and sulfuric. Just the first proton. So with weak acids, you'll have actually the elephant will switch sides and go over here, and then maybe you have like a baby elephant over, actually not really an elephant, something that still stays on the teeter totter, not like a little kid. Okay, so something that would stay here, like maybe a dog, maybe like a big dog. Okay, so it still stays there. Okay, but it's definitely favoring this side for sure. Okay, and then with different weak acids, so that would be one that's like really weak, like 10 to the negative 11th. Okay, if your Ka was like 10 to the negative 4th, then it might not be an elephant. It might be like a gorilla and a dog, like a regular sized dog. Okay, so I have an example. Okay, where it says use Ka to or Kb. And this on this slide, I'm not going to look at bases. In fact, we're not going to really look at bases for another couple of days at least. So use Ka or Kb to determine acid or base strength. So I'm going to write dissociation reactions, name the acid, and then I'm going to show if it's a polyprotic acid, meaning more than one proton, I'll show stepwise dissociations, and then I'll write the Ka for each step. Next, and lastly, I'm going to rank them, assuming they're all 1 molar. So I'll rank them in terms of acid strength. So, a key thing is a misconception is sometimes students will look at the pH and then try to judge acid strength based on the pH. So that's pretty common misconception. The strength depends strictly on level of ionization. So you could have a weak acid, but it could be like very concentrated. Like you could have like 18 molar acetic acid. Okay, and it will have a much lower pH than like a really dilute, like 1 times 10 to the, I mean, I don't have the numbers in front of me. Like if you have like a dilute sample of hydrochloric acid, which is a strong acid, the concentrated weak acid will have a lower pH than that one. So notice that base strength is strictly looking at Ka, and really nothing else, just level of ionization, like how much of it goes to the ion side. So okay, so I just have a couple of these. So here's 4 of them. So it says stepwise. So here I have a polyprotic acid. This is sulfurous acid. So we write the first dissociation like this. So I'm just going to break off one proton. And almost from now until the end of the year, in fact, this goes so fast that a lot of textbooks, they don't even show H3O. So in the future, and really the amount of H plus you have will be equal to the amount of H3O that is formed. So I'm probably not, actually, I'll tell you now, I'm not going to be writing H3O just to simplify the equilibrium expressions. I'm just going to write H plus. The previous slide was probably the first and last time that I'll actually write out H3O. So this is going to be formed. So I'm just going to break off one proton. So one of them will stay attached to the S3O, to the sulfite ion. So this is going to be HSO3, and it'll actually be a -1 because the sulfite ion is what this all comes from. So this can hold two H's. And if it's holding one, it'll still have a -1 charge. So I looked this up previously. The Ka1 for this is 1.7 times 10 to the negative second. The next dissociation is going to be this. We'll go on to dissociate one more time. So I'll use this on the next step, the successive step. Okay, so then I'll take this proton off, and then I'll show just the bare ion like that. Okay, and then the Ka2 is going to be 6.4 times 10 to the negative 8th. And it says to name it, so this is sulfurous acid. Remember the ending, this comes from sulfite. The ending is ite. So when you go to name the acid, it's us. Okay, and if your ending is 8, like you'll see when there's a lot of oxygens on your anion, then you'll get like the max number of oxygens, then it's going to have the 8 ending. So for example, nitrite is this ion, and the acid it makes will be nitrous acid. This is nitrate, and the acid this makes will be nitric. So this gives you us when you name it, and this gives you ic when you name it. So HNO2, I'll write the dissociation for this. And then the Ka, which I looked up previously. Something happened here. I ended up... Let's go back. Okay, so this is 4.5 times 10 to the negative 4th. Okay, and the next one is, so here is where I almost started writing a dissociation reaction, and then it just kind of hit me that, wait a second, this is one of the strong acids. So I'll write Na. There is no dissociation. Actually, there is a dissociation, right? It should not have equilibrium though. It should just have one arrow plus ClO3. Okay, and you could waste all the time in the world Googling the Ka for chloric acid. And the reason you might be Googling that, the reason you might be Googling is because you didn't memorize the 7 strong acids. So, there's an easy way to do things, and then, the painful way. So you could spend all this time Googling that, but if you memorize them, then you'll know this is a strong acid. Okay, and then we just write Na. So HIO is not one of the strongs, it's a weak. So I'm going to go like this. The Ka is 2.3 times 10 to the negative 11th. And the name for this is, I forgot to name this one, it's nitrous acid. And this one is called hypoiodous acid. You may need to review from, I think it was like the second week of school when we went over nomenclature. So it says the last thing here is to rank them in terms of quantity of ions. So we're going to, in other words, acid strength. So our strongest one is HClO. Okay, so followed by the first of this one, so H2SO3. If I look at the next strongest Ka. So the one that's next favorable to the right side is nitrous acid, so HNO2. And then this one is dead last in terms of strength. So that one's going to be very, very heavily favored on this side. So not much at all on the ion side of that one. So the next one is the dissociated sulfurous ion, and then the next one is hypoiodous. Okay, so I have a very similar your turn question. Okay, it's on the following slide. So you're doing pretty much what I just did on this one. Okay, so I'll see what you guys come up with tomorrow. It's the end of the video.